so I think we should get started. So we've got two excellent talks again this month. Our first speaker is Jan Taucher from GMR, and he's going to be talking to us about the silicon cycle in a changing ocean. So without further ado, over to you, Jan.
Yeah, thanks, Adrian, and thanks for inviting me to present here. So my name is Jan Taucher. I'm from GMR in Kiel, Germany. And yeah, today I want to talk a bit about the silica cycle in a changing ocean, especially focusing on the impacts of ocean acidification and also the implications for diatoms, and also a bit about the biological carbon pump. So yeah, if people are interested, we recently published this work in Nature, but yeah, today I want to also take the chance to dive a bit into more detail and hopefully have some nice discussion. So yeah, I want to start with some basic info on diatoms and why they are important. So I guess most people here are familiar with them. But yeah, diatoms account for approximately 40% of primary production in the ocean. And their most prominent feature probably is that they build opal shells from silicic acid, most likely for protection against grazers. And these shells also serve as mineral ballast for the sinking particles. And also, diatom cells are usually larger than other phytoplankton, so the cells range in size from tens to hundreds of micrometers, and chains of diatoms can even get much longer. So yeah, altogether, diatoms account for a high biomass and produce large and fast-sinking particles, so they are usually considered an important driver of the biological carbon pump. Which is also illustrated here in this nice graph from a recent review, yeah, where you see that the contribution of diatoms to the biological pump is quite substantial, and of course it's also regionally variable. So so what do we know so far about responses to ocean acidification? And yeah, ocean acidification, as you probably know, is just a word for the shifts in carbonate chemistry and the drop in pH that occurs to the increase in atmospheric CO2 and its uptake by the ocean. And yeah, this has been subject of research for more than a decade now, and there have been some tons of experiments and also several meta-analyses which found that basically diatoms are yeah, either positively or not affected by ocean acidification. So neither on the physiological level or also on the community level. You see that yeah, growth responses and also photosynthesis rather shows yeah, positive effects, and also on the community level there's yeah, most of the evidence points towards no or positive effects. So basically the consensus so far is that diatoms are resilient or might even benefit from ocean acidification. But I mean, the fate of diatoms is also linked to the silicon cycle and how it's potentially changing in the future, because diatoms need silicic acid to build their opal shell. And the concentration of silicic acid is actually low in most parts of the ocean, as you see here, except for these HNLC regions. So diatoms are usually limited mostly by silicon. And besides the absolute nutrients concentration, what's important is also the availability of silicon compared to other major nutrients like nitrate. And it's usually assumed that an SI to N ratio of 1 or higher is optimal. So this corresponds to surplus silica compared to nitrogen of 0 or larger, which is often defined as that SI star. And you see that this is also regionally very variable. And this relative availability of silicon versus nitrogen is also linked to the sinking of biogenic particles, because of course production strips out these nutrients from the surface ocean, and then the transport of sinking particles to deeper water layers removes these nutrients to depth, where they're then converted back to their dissolved forms. So this SI to N ratio of exported material in combination with ocean circulation, really determines the large-scale distribution of nutrients and diatoms. And a key region in this respect is the Southern Ocean, because it generally plays a key role in nutrient cycles. So due to nutrient trapping, about half the global nutrient inventory is regenerated here. And also the formation of deep waters or mode and intermediate waters is a major source for nutrients in primary production in large parts of the global ocean. And so what happens usually is that there's upwelling of circumpolar deep water on the Antarctic front. And this water then moves northwards, where it's subject or is a source to production, mostly by diatoms. So there's production with a high SI to N ratio. And basically the SI to N ratio of production export determines how much of these nutrients then is left over in these water masses that move northwards and are then subducted as mode and intermediate waters. So basically this I to N ratio of uptake and export is really a globally relevant process, also determining productivity in large parts of the global ocean. And so far it's basically unknown if and how the silica cycle and SI to N ratios will respond to a changing ocean. So in order to understand and get a better idea on the responses of the silicon cycle to ocean acidification, we conducted several in situ mesocosm experiments in different oceanic regions using these large enclosures here. And basically what we do then is we enclose natural plankton communities and then simulate different levels of ocean acidification. And the nice thing is that with this approach, we're able to differentiate also between effects on production, so responses of diatoms or plankton communities, and between processes of export and degradation. So, for instance, changes in the composition of sinking particles, which are captured here by these sediment traps. So we ran a meta-analysis on these data sets, which you can see here in these figures. So on the left is the normalized effect size, and on the right are the probability densities for the raw data for ambient and ocean acidification conditions. And we actually found a surprisingly consistent increase in SI to N ratios of export under simulated ocean acidification. So the overall effect was about an increase of 17% in SI to N ratios for ocean acidification levels, end of century ocean acidification scenarios. And what's also interesting is that this effect only occurred in the sinking material. So we also looked at responses of phytoplankton communities and the suspended POM in the water column, but there weren't any effects there. So this suggests that this ocean acidification effect emerged during the sinking of particles. Now, how can we explain this? So generally, seawater is corrosive to biogenic silica. So diatom-derived particles dissolve once they start sinking. So usually when the cells die or when the bloom is terminated, this organic coating around diatom frustules is degraded by bacteria, and then the frustule is subject to dissolution. And this dissolution rate is mostly controlled by temperature, but also to some degree by pH. So there's a few older chemical studies that show that per unit pH, there's a roughly 60% change in dissolution rate of offal. So I marked this here in these red boxes on these graphs, which correspond to a unit pH roughly in the range of where ocean acidification also occurs. And these early findings also match remarkably well with what we found in our mesocosm experiments, so where we had a 20% change about roughly for 0.3 pH units. So this strengthened the evidence that the silicon to nitrogen responses to ocean acidification that we found in the experiments were not due to some biotic responses by the community, but were really driven by this chemical process and its sensitivity to pH. So then we wanted to know, okay, can we see this mechanism also in present day observational data, for example, from sediment traps? And a way to look at this is to look at vertical profiles of the silica content of sinking particles, so at the elemental composition of fluxes, because generally the silica dissolution is slower than the remineralization of carbon and nitrogen. So usually particles are enriched in silica with depth, which is then reflected in the elemental ratios. And this so-called silica pump enhances the loss of silica from the surface to the deep ocean compared to nitrogen, which is more readily recycled by grazing and the microbial loop. So this results in this silica surplus, or this SI star, which I showed earlier, which is very high in the deep ocean, but basically around 0 or 1 near the surface. So what we did then was to analyze a global compilation of sediment trap data, which was published a few years ago by Mo et al. And cover sediment traps and also lots of time series around the globe. So in this data set, we then looked if there's a relationship between the enrichment of sinking particles with silica, so the increase in SI to N ratios with depth, and pH. And indeed, we found such a relationship, as you can see here on the lower plot, which basically shows that at lower or at decreasing pH, the SI to N increase with depth is stronger. So the enrichment with silica is enhanced, which indicates that silica was dissolved more slowly than nitrogen at lower pH. So basically, this confirms the conclusion that we also derived from our mesocosm experiments. And it might be a bit surprising that this influence of pH on the silica cycle has so far been overlooked or neglected, because as I've shown earlier, there were a few chemical studies already on opal dissolution, which showed that there's also some role of pH. But probably it's been considered unimportant because in the present day, ocean temperature is really the major driver for opal dissolution. So I've plotted here some global averages for profiles of temperature and pH. And as you can see, the vertical gradient for temperature is approximately 15 to 20 degrees, which corresponds to a 3- or 4-fold change in the dissolution rate of silica. And for pH, the present day gradient is about 0.3 or so, which corresponds to a 0.2-fold change in dissolution rate only. So in present day conditions, temperature is really the dominant driver, with 10 or 20 times stronger effect. And it's also important to say that under present conditions, both gradients work in the same direction. So they both decrease the dissolution rate with depth. Now, under future scenarios of warming and ocean acidification, this picture changes completely. So the relative importance of pH and temperature changes really substantially. So when we assume over the next centuries a warming of 3 to 4 degrees, and a drop in pH of between 0.4 to 0.6 units. This corresponds to a warming effect on opal dissolution by 1.4-fold versus a pH-driven decrease by 1.8-fold. So now both effects are really on the same order of magnitude, or actually the pH effect is stronger. And both effects are antagonistic. So the warming effect would drive towards a faster dissolution, but the pH effect towards a slower dissolution. And actually, when you look at this right plot here, which shows an idealized flux, you see that this, the combined effect actually also results in a weaker flux attenuation of opal. So the effect of decreasing pH overcompensates for the effect of warming on global average. So what does this mean? What are the consequences on a global scale? And in order to assess this, we implemented this pH sensitivity of silica dissolution into a global model. And this is just a short video. I'm showing a latitudinal section of the global ocean. And you can see that in the late 21st century or so, that there's a loss of silica from the surface ocean and transfer to the deep ocean, which then accelerates. And on the next slide, we look at this in a bit more detail. So this is also a latitudinal section, but split into the Atlantic and Pacific and centered around the Southern Ocean. And you can see here again that there's a transfer of silica from surface to depth, which is strongest in the Southern Ocean, where also where there's the highest productivity of diatoms and of export of opal. And the slower dissolution of silica here enhances the silica trapping. So silica is transferred to depths beyond 2,000 or 3,000 meters here in the region south of the Antarctic front. And then it enters Antarctic bottom water and basically stays trapped in the deep ocean. So a small fraction of it is also entrained in circumpolar deep water, which is then upwelled again to towards the Antarctic divergence. So this kind of creates a cycle of particle export with slower opal dissolution, so more effective silica transfer to depth, and upwelling of water that's enriched with silica. But the latter process is really not enough to counteract the stronger silica pump. So in overall, we really have a depletion of silica in the surface layer and hence trapping of silica in the deep Southern Ocean. And as I mentioned earlier, the Southern Ocean plays a key role in global nutrient cycles. So this trapping really has global scale consequences. Because also the intermediate and mold waters leaving the Southern Ocean are then depleted in silica, and they get upwelled again somewhere in the Northern Hemisphere where there's further production by diatoms, and which further depletes the water from silica basically. So there's really a global scale loss of silica from the surface ocean and trapping in deeper waters. So what are the consequences of this silica trapping in the deep ocean? Well, obviously in many regions, silica becomes limiting. So as a consequence, we see a strong decline in diatoms in the model, which amounts to -13 to -26% on the global average. And the strongest loss is in the Southern Ocean and in the tropical Pacific. So these are also the regions where in the model diatom productivity is highest and also where silica now becomes limiting. And you can see this also on the right on this integrated change across latitudes, that about 50% or so of the loss of diatoms occurs in the Southern Ocean. And these results are really in sharp contrast to the current view about diatoms and how they respond to ocean acidification, which I described in the beginning of my talk. So until now, most people have thought that diatoms might rather be a winner of ocean acidification. But now, when we take into account this global feedback mechanism, so an abiotic mechanism that's not related to responses of diatoms or plankton communities, we actually find the complete opposite. So this is really in some way also a nice example of basically how unexpected responses of marine biota or biogeochemical cycles to ocean acidification can be altered or even turned completely upside down on larger scales due to unforeseen feedback mechanisms. And in this case, it's ocean acidification, but I guess this this might also apply to other changes like warming or so, where there's just maybe processes that we hadn't taken into account so far. Now, I want to briefly touch about some on the potential implications for the carbon cycle and the biological pump. So now basically what we found is that the decrease in pH results in a slower dissolution of silica. So for particles produced by diatoms, this would lead to slower silica dissolution, but the slower silica dissolution would enhance the protection of organic material that it's sinking, so protection against remineralization, and potentially also enhance the ballast effect on sinking speed. So on this micro scale, on individual particles, you might think that the biological carbon pump becomes more efficient. But then again, our model results also showed that there's a large loss of diatoms around the globe. And probably this would also come along with a change in food web structure and a lower proportion of carbon export by diatoms, of course, which would then maybe result in lower sinking speeds, so less mineral ballast and also less protection of the silica shell for the particles, so maybe higher remineralization rates compared to diatom-derived material. So yeah, these are basically two opposing effects, and from our results or from our model simulations, it's really hard to tell because like most Earth system models, the model is really simplified. So in our model, the loss of diatoms is compensated by other smaller phytoplankton, so there's little effect on total productivity and carbon fluxes. But I would assume that in reality, there are changes in food web structure and grazers and so on, which would also in turn affect carbon export. So this is really something that needs to be tested in the future in more complex models where such changes are better accounted for. And in order to get a better idea, basically, which of these processes becomes dominant and what the net effect for the biological carbon pump is. So to conclude, we found in the study various independent lines of evidence, so from mesocosms and ocean sediment traps, and also from earlier chemical studies, that ocean acidification enhances the transfer of silica from the surface to the deep ocean by slowing down the dissolution of sinking silica particles. And this loss of silica from the surface ocean in turn then leads to a global decline in diatoms, which really sharply contrasts our prior knowledge from experimental work. And as I just said, for the future, I think it would be really important to examine in detail the repercussions of these changes for food webs and the carbon pump. And I was planning to get in touch actually with other modeling whose models might be more suitable, and maybe we can implement mechanisms on the particle scale and also on food web changes in order to get a better idea of what these changes might imply for the biological carbon pump. So that's basically all I was going to say. Thanks for your attention, and I'm happy to take questions.
Thank you, Jan. Excellent piece of work, going all the way from the mesocosm to the global. That is very nice indeed. So I'll throw it open to the audience. If anybody has any questions, feel free to type something into the chat, or if you want, I can open the microphone if you just want to sort of raise your hand.
I'm worried that we've lost Adrian, potentially.
Yeah, let's see if he's coming back. But
so I'll ask a question, Jan. In your model, are you tracking the sinking of the biogenic silica and how it's interact? Because obviously the anthropogenic perturbation imprints on the ocean as it gets at the surface, and then as it gets transferred into the interior through the water masses. You didn't talk about that. Not all of the ocean is seeing the same change in pH and temperature.
You mean if there's regional differences, or?
Yeah, so I mean, the only place where perturbations in warming in the interior and acidification in the interior are places where water masses are subducted. I guess they happen to be places also where there's strong silica fluxes. Is that part of the story behind the regional picture you get on the change in the silica distribution?
No, I mean, I guess it's really mostly, I mean, the pH changes in the surface 100, 200, 300 meters basically all around the globe. I think I had this in one of the plots, and I think that's really where why basically on the global scale the flux may penetrate deeper. So it's really not restricted to one region. I mean, of course, we see it most obvious in those regions where there's high diatom export, or especially in the Southern Ocean, just because it plays such a central role as a nutrient hub. But I think basically the process itself should occur more or less everywhere, because I mean, of course there's places where your pH changes stronger or drops earlier than in other regions, but it's still I would say it's a globally uniform thing that's happening.
Okay.
Thank you. Yeah, sorry if I disappeared briefly then, my connection just dropped out. So I think we've got time for another question. Nick Cassar has got a question. Nick, if you'd like to ask.
Yeah, thanks for the nice talk. Just, is there any evidence, have you looked at the geological time record to see if there's evidence of this in the past, of this process in the past, glacial, interglacial, but even before that, before the Pleistocene?
No, good question. I mean, I know, of course, that Brzezinski paper that looks at basically the role of silica to nitrogen ratios, but I think they don't mention pH or so. I think mostly the paleo studies are about warming or also changes in the iron cycle, but I'm not aware of anything that looked into pH effects. But I mean, in theory, it should, right? I mean, it's the question is, I mean, if you really have strong temperature fluctuations, also then which process dominates? But and I don't know. I mean, I'm not so familiar with how far into the past you can reconstruct ocean pH, and if that's something that we could test. Do you know anything more about this? Or
no, I was trying to figure out if let's say you have very high CO2, how that influences the abundance of diatoms, high CO2, low pH, the abundance of diatoms versus periods with lower CO2. And that should be visible within sediment core.
Mm-hmm. Yeah, it would be interesting to look at that, definitely.
So thank you once again to Jan. Absolutely excellent talk. If people have any questions for him, then I'm sure he'd be willing to hear from you. Send him an email. But thank you very much, and we'll move on to our second